Okay, Laplace transforms. So in this lecture, we'll define them, provide some notation. We'll show that it's linear. We'll define what the inverse Laplace transform is and have a little bit of a table. Laplace transforms are a useful way to solve differential equations. We define it. If you have a function f of t, the Laplace transform is this integral. Note that when you integrate with respect to t, right, that's the dt part, you then plug in 0 and infinity for t. So the result of this integral will be that the t's will go away because you evaluate them from 0 to infinity, and then you'll be left with the s. So you get a function of s. We also use the squiggly L to denote the Laplace transform of a function. Generally, a small letter, like a little f, is a function of t. The capital letter, the capital F, that's the Laplace transform, a function of s. So we want to find Laplace transform of exponential functions, sines and cosines and polynomials, because when we solve our differential equations, we often get these functions. So what's the Laplace transform of e to the at? The Laplace transform of e to the at, and this thing is supposed to be that squiggly L, I don't draw it very well, is the integral from 0 to infinity of e to the at, because that's my function, times e to the minus st, which is part of the definition of the Laplace transform dt. And I can write that as the integral from 0 to infinity of e to the a minus s times t dt, just by collecting together my two exponentials. And then I'm going to actually write it like that, just change the order by taking out this minus sign. Okay, so u equals s minus a times t, du equals s minus a, because those are not t's, dt, or dt equals du over s minus a. So after the substitution, the integral becomes 0 to infinity e to the minus u du over s minus a. If we do the integration, we get the s minus a comes out. The integral of e to the minus u is minus e to the minus u evaluated from 0 to infinity. Now, how do we evaluate the infinite limit? So if you remember back to, I think, Calc 2, we take the limit as b goes to infinity of e to the minus b, and that equals 0. So this becomes 1 over s minus a times, well, there's a minus sign there, minus 0 minus 0 minus 1, I think. Got too many minus signs floating around. So we'll get rid of this. 1 over s minus a. And we get a 0. And then we get a minus sign here, but a minus from the evaluation. And so that gives me a plus 1, which is 1 over s minus a. So that's the Laplace transform of e to the at, 1 over s minus a. And getting s's in the bottom is actually quite characteristic of the Laplace transform. What's the Laplace transform of f of t equals sine bt? Laplace transform of sine bt is equal to integral from 0 to infinity the function, which is sine bt, b is just a constant, e to the minus st dt. And what is that equal to? You have to do integration by parts twice, which is kind of a hassle, but it's e to the minus st s sine bt minus b cosine bt And then I close that parentheses, and it's all over s squared plus b squared. So to do that integration by parts, what I did is I actually went and looked it up on Wolfram Alpha because it's a pain to do that by parts. And it's evaluated from t equals 0 to t equals infinity. So Wolfram Alpha is a very useful thing, and if you haven't used it, you should go check it out. So what's the Laplace transform of sine bt? That's this thing evaluated from infinity to 0. Now, if I let t go to infinity, I'm not actually going to do the formal stuff there, but if we let t go to infinity, this goes to 0, right? So we get 0 minus, and then if we let t be 0, we get 1 times s times sine of 0, which is 0, minus b times cosine of 0, which is 1, over s squared plus b squared. And so what do we end up with? Minus minus makes that a positive. This is 0, so we just get b over s squared plus b squared. And so that gives us this. So we took these limits to show that this is equal to 0 to get that to go away. What's the Laplace transform of sine of bt, cosine of bt, sorry. So how do we find the Laplace transform of something? The Laplace transform of a function is the integral from 0 to infinity e to the minus st cosine bt dt. And again, using Wolfram Alpha, we go and look this up. We find out that this integral is e to the minus st times the quantity b sine bt minus s cosine bt and parentheses all over s squared plus b squared from 0 to infinity. So because the limit is t equals to infinity, e to the minus st equals 0, when we evaluate this at infinity, this goes to 0, which basically kills everything off because 0 times anything is 0. And so we just plug in this 0 to get this equal to minus 0 minus the 0 coming from this limit. Plug in 0. This is 1. Sine of 0 is 0. We get a minus s times 1 over s squared plus b squared. One thing to note is that I'm being a little bit loose with the limits, right? This limit really requires that s be positive, and as does the limit here. And the limit here requires that s be bigger than a to get this limit to work. We are interested in Laplace transforms as symbolic tools for solving differential equations rather than worrying about the exact domains of the functions we get. So we're just going to let that slide. So the Laplace transform is a linear function. The Laplace transform of k1 f of t plus k2 f of t equals, well, it's the integral from 0 to infinity of e to the minus st times k1 f1 plus f1 f2 plus k2 f2 dt. But we know that we can break that into two integrals, e to the minus st times k1 f1. k1 and k2 are constants here. f1 and f2 are functions. Integral from 0 to infinity of e to the minus s2 k2 f2 dt. And then the other thing we know we can do with integrals, because integrals are linear, right? Linearity means I can break the addition up into two things, and then it also means I can factor out the constant. So I get this set of integrals, but this thing is just the Laplace transform of f1. And then this thing is just the Laplace transform of f2. So we can do what we usually are used to in calculus when we do integrals and derivatives, which is we can take the integral or derivative of a sum multiplied by constants by taking the integral or the derivative of the individual functions, multiplying by the constants, and then adding them up. So we can do the same thing here. If you want the Laplace transform of this sum, take the Laplace transform of f1 and the Laplace transform of f2, multiply by k1 and k2, and put them back together. So if we want the Laplace transform of this, we can just say, okay, we want the Laplace transform of e to the minus 5t, and then we'll multiply that by 3, and then we'll take the Laplace transform of cosine 7t and multiply that by minus 4. And this is 1 over s minus 5, because we've seen that before. The Laplace transform of e to the at is 1 over s minus a, and we have a equal to minus 5. Minus 4, well, the Laplace transform of cosine bt that we've seen above is s over s squared plus b squared. So this is minus 4 times s over s squared plus 49, because 7 squared. So we get 3 over s plus 5 minus 4s over s squared plus 49. Okay, so we just need to find the Laplace transform of that, and the Laplace transform of that, and multiply by the coefficients. Now, finally, the inverse Laplace transform. What function f of t has this Laplace transform? So here's a Laplace transform. We want to know what this is. Well, we know that the Laplace transform of, let me write some of these down, Laplace transform of e to the minus e to the as equals 1 over s minus a. So this looks like it should be the Laplace transform of e to the 3t. Because if we take t equal to 3, if we take a equal to 3, take the Laplace transform of e to the 3t, we should get that. This, we're not quite sure of. It's got s minus 1 and s plus 1 in the bottom, so we think those should be Laplace transforms of exponentials. We can do partial fractions. To split this apart. And if you do partial fractions to split that apart, you get 2 over s minus 1 minus 2 over s plus 1. Great, and so this we recognize then as being the Laplace transform of 2e to the t, because we look at this and we see a equals 1. And this is going to be the Laplace transform of 2e to the minus t, because the plus 1 means this is really s minus minus 1, and so a is minus 1. And the other thing we need to know is that the Laplace transform of sine of bt equals b over s squared plus b squared. So this last term must be sine of 10t, because this means b equals 10, b squared is 100. So what do we get there? We've got the Laplace transform of e to the 3t plus 2 e to the t minus 2 e to the minus t, and remember that minus sign there, plus sine of 10t equals, oops, we'll put a bracket there, equals what we've got here, 1 over s minus 3 plus 4 over s minus 1, s plus 1 plus 10 over s squared plus 100. So if we know what the Laplace transform is, we can figure out what original function it is. And so this is an example of an inverse. And so the inverse notation we have is Laplace transform inverse of 1 over s minus 3 plus 4 over s minus 1, s plus 1, plus 10 over s squared plus 100. Inverse Laplace transform of that is e to the 3t plus 2 e to the t minus 2 e to the minus t plus sine of 10t. Great. So, in other words, if I have a function and its Laplace transform, the Laplace transform takes me this way, the inverse Laplace transform takes me that way. Partial fractions. Use Wolfram Alpha to do those. On tests, I'll give you a table of useful partial fractions to use. So, inverse Laplace transform. So what we've seen here is e to the at has this as its Laplace transform, but that also means that, oops, the Laplace transform takes me this way. That's the Laplace transform. The inverse Laplace transform takes me that way. So the inverse Laplace transform of this is that, and there's sine bt, cosine bt.